Here is another kind of tricky example that comes up in this problem set homework where you are given information about a boat going downstream or upstream, or it might be a plane in the air going with the wind and going against the wind. Both of those situations sort of work the same way. Or it could be like a person walking on a moving sidewalk, maybe, going in the direction, and then they turn around to walk opposite the direction of the moving sidewalk. Anyways, let's see where we need to start with this. We're given how long it takes. It takes 1 hour to go 13.5 miles downstream to a trading post. And the return trip, which is the same distance, going upstream, takes 3 hours. And we need to find the speed of the boat in still water and the speed of the current. So the way to approach something like this, or any kind of word problem, is start by making up variables that stand for the quantities the question is asking for. And the general principle with anything like this is that if you're going downstream in the same direction as the current, then the speed you actually move is the combined speed of the boat that it would go in still water plus the speed of the water itself. So in other words, when you're moving in the same direction as the current, the total speed you go, you can add them up together to get the total speed. And the opposite is true when you're going upstream. So the water is still going in the same direction, but you're going in the opposite direction. Your speed, your combined speed, is going to be slower. It's going to be the speed your boat is going, but with the current subtracted from that. So that helps you fill in the table like this. This is a table I copied from the book, and the general principle is that rate times time is always equal to distance. So you multiply these and get the distance. And the downstream rate is another word for speed here, the downstream speed is c plus b, or you can write that as b plus c if you want. The upstream speed is b minus c, and the times are different. The time to go downstream was only 1 hour, so that's just 1. And the distance that you go in that 1 hour was 13.5. And upstream, the distance you go is still 13.5 for the return trip, but it took 3 hours. So when you do this rate times time equals distance, you get two equations that look like this. You do b plus c times 1 equals 13.5, and b minus c times 3 equals 13.5. And that gives you two different equations with two different variables that you can solve in the normal way, either using elimination or substitution. I'm going to choose to use elimination for this one because I notice there's the first one just comes out to b plus c times 1 is just b plus c. The second one, once you distribute the 3 in there, it's going to be 3b minus 3c, but you don't have to do that because you could just make this be negative c by dividing both sides by 3. And multiplying by 3 and dividing by 3 cancel each other out, so that makes the second equation look like this, because 13.5 divided by 3 comes out to be 14.5. And I set it up like this so that we could see that we can just add up the left sides of the two equations, add up the right sides, the plus c minus c will cancel out, and we'll just get 2b equals 13.5 plus 14.5 is 18, and then we can divide both sides of that by 2 to get b equals 9. And once you know what b is, you can plug that into one of the original equations. Let's say the first one here. That's going to make that become 9 plus c equals 13.5, and you could just subtract the 9 from both sides, and you'll get c equals 4.5. So that sounds reasonable, that the speed of the boat might be 9 miles per hour and the speed of the current is 4.5 miles per hour. That would make her go a lot slower. Hopefully when she gets to the trading post the next time, she'll buy a faster boat so she doesn't have to spend 3 hours going back home. So there's the answer for that. Good luck doing these on your own. They are tricky. There's a couple of them in the problem sets. I'll let you try those then.